Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet, Reconnecting with Carbonyls. A quick review. Okay gang, so you know the drill. A worksheet solutions walkthrough is where you've attempted the practice, worksheet on jOeCHEM. You may have looked at the answers, compared what you got versus what I put as the answers, and you're looking for an explanation. Well, you're in the right place. So as we wade our way back into the land of carbonyls, we attacked them with Grignards back in jOeCHEM 1. We're about to do a whole bunch of new stuff with them here in jOeCHEM 2. So this is just a little refresher worksheet. We're going to oxidize, we're going to reduce, talk about physical properties, but enough of my blabbering. Let's talk about the worksheet. Okay, gang, this is a quick worksheet with 2 problems, so let's just run right through it and get through what will hopefully be the shortest solutions walkthrough on jOeCHEM. Okay, so if we take a gander at problem 1, there's 3 parts to it. I promise they're all really quick, or maybe you already know that. So in problem, part A of problem 1, we are tasked with looking at these 4 structures and ranking from highest to lowest the boiling points of them. So remember, when you're talking about boiling point, right, when you're heating up a liquid, you're actually overcoming the intermolecular forces, the forces between the molecules. If you're heating them up, right, when you're boiling, then you're going to cause the solution or solid, whatever you're working with, solution to gain more energy. The molecules start moving farther apart. You start to transition from a liquid to a gas. So the stronger the intermolecular forces, the more heat you'll need, the higher the temperature required to boil, the higher the boiling point. So we're looking for things like molecular weight, right, for dispersion forces, or dipole-dipole, polar bonds, and the one that reigns supreme, hydrogen bonding. So I think you can agree 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All of these have the same amount of carbons. So I think you can see with this carboxylic acid, we have not just the dipole-dipole, but we can hydrogen bond a whole heck of a lot. Over here, no hydrogen bonding. Here we have hydrogen bonding, dipole-dipole, dipole-dipole as well. Here we just have regular old dispersion forces. So that butane definitely has the lowest boiling point. Now, we can see we can hydrogen bond because of what's going on here and here. So as a result, the aldehyde, although it looks pretty good and it almost can trick you into thinking it can hydrogen bond, it can't. This comes in at second. Now, here's the tiebreaker. Every lone pair and partial positive hydrogen in a solution where you can hydrogen bond is a hydrogen bonding site. So over here on butanol, we have 2 lone pairs and then the hydrogen itself. So there are 3 hydrogen bonding sites. Over here, however, we have 1, 2, 3, 4, and then 5. So there's 5 positions over here. The carboxylic acid can hydrogen bond much more than just regular, butanol. So butanol comes in second. That's number 3. And coming in at 4th, the highest boiling point is the butanoic acid, okay? Moving on to B. We're given this Grignard reaction. We see we have a carbonyl-carbon, and remember, at the core, this is a partially positive carbon because it's double bonded to this oxygen right here, and we know we can draw resonance where we give the oxygen the electrons straight up. That's all that goes to saying this is a very strongly partially positive carbon. We know we have a very nucleophilic carbanion with our methyl Grignard here. So the problem is saying we get a racemic mixture. Why is that the case? Well, the point being is that, and you'll see that I drew this on the worksheet where I forget whether I wedged and dashed which groups. Maybe I dashed the ethyl. It doesn't matter. This was me trying to draw in a trigonal planar fashion. Yes, this is trigonal planar, right? And if you drew this like this, that's fine as well. I just really wanted to highlight that, remember, with trigonal planar, you have 3 things like this. So to really kind of illustrate that, I just drew it like this, where this green marker would be a wedge and the purple would be a dash, okay? So the methyl Grignard doesn't care whether it comes from the top or the bottom, right? That's an sp2 trigonal planar carbon. Because it's trigonal planar, that means flat. So the methyl can approach from either side, and as a result, that's why we get an even mixture of racemic mixture of wedge here. And I'm now realizing I forgot this right there, so I apologize for that. That made a difference. I was having a small freak out. The OH being a wedge, and that's our only stereocenter, which is why we get a racemic mixture. We could also have this as well. Okay, just long-winded way of saying we can approach from the top or the bottom because trigonal planar geometry, because we have the carbonyl. Okay, now down here, we are tasked with explaining when undergoing attack from a Grignard, I believe, which of these substrates, rank them from how fast the reaction goes, slowest to fastest. Remember, the easier this Grignard can approach the carbonyl carbon, the faster this reaction will go. So I think you can see, this is just formaldehyde. It's only just it's a carbon with 2 hydrogens, flanked by 2 hydrogens. Here we have acetone, 2 methyl groups. And then here we have an aldehyde with just 1 CH3 off of it. I know these aren't very guarded in terms of steric hindrance, but there's virtually nothing that would prevent any nucleophile from coming in to attack the carbonyl carbon. So you go by the least substitutedness. This will absolutely react the fastest with a strong nucleophile. This will come in second, and this will react a little bit more slowly. Of course, if we had giant groups like T-butyls off of here or here, that would be really slow things down. Okay, gang, that's problem 1. Let's jump into 2 and finish the walkthrough. Okay, gang, rounding out this worksheet with problem 2, we can see we have 6 either complete the reaction questions, provide the reagent, or fill in the, fill in the reactant, or fill in the reagent problems. So, looking at this very first one, and they're all oxidations or reductions, okay? So if we take a look here, I hope you can see we have, get my black marker back, primary alcohol, and you can either see, whether you call it the Jones reagents or sodium dichromate and H2SO4, this is our very aggressive oxidizing reaction here. We're going to either take a primary alcohol all the way to a carboxylic acid, or, if it's secondary, we're going to take it to a ketone. So, you can see this is primary, so we're absolutely going to oxidize as far as we possibly can. So, I'll keep my benzene ring here, which is really just decoration, and we get the carboxylic acid. Okay, so now in the second problem, now I think you can see primary alcohol, but remember PCC. It definitely helps us oxidize alcohols, but it's not nearly as aggressive as the Jones or, the sodium dichromate H2SO4. We're just going to get an aldehyde here. So remember, just don't lose any carbons. 1, 2, 3, 4. 1, 2, 3, 4, and then I have the methyl group right there. We're good to go. Now we see that we've done a sodium dichromate H2SO4 oxidation, but we have the product. So remember, just walk this back. We see carboxylic acid here, and we see a ketone here. So we must have had alcohols at those positions. Just remember to make sure that top one is a primary alcohol, and then just don't lose any carbons. There's my OH down here, and I'm almost bumping into the problem below, but 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then on 2 we have the methyl group. Okay, down here you can see we have NABH4 and ethanol. It's just a simple reduction. Okay, and remember, when you see this, you're really seeing hydride, and you need to be wary of creating stereocenters and racemic mixtures because hydride will attack above and below, but we don't have to worry about that here. We can actually just write this product, and that's why I did so on the answer key, just like a straight line, because this is not a chiral center. It's not a stereocenter. Sure, you could absolutely put wedge and dash, but putting plus an enantiomer would not, someone could maybe dock you a point or two, because this isn't a stereocenter, so it's achiral. It doesn't have an enantiomer, okay? Because it's not attached to 4 unique things, right? 1, 2, the ring. We have equivalent groups on both sides. Okay, now down here, we have lithium aluminum hydride and hydronium in excess. So remember, this is another reduction. Absolutely, you should think of hydride just coming in and attacking both positions. Okay, so be careful. So we have 1, 2, 3, 4, 5 carbons. Let me at least get that down. So I know I have an OH over here, and again, I don't have to worry about wedge and dashness because we're not attached to 4 different things. There are 2 hydrogens here. But over here, careful, because you do you do produce a stereo center, okay? And since that's the only stereo center we produce, and we know that it's gonna be 50% wedge, 50% dash, here's where we can write plus an enantiomer, because you will have another structure, or again, this is the same, it's just a straight line, but then this will be a dash. So this is where you have to watch out. Just ask yourself, did I create a stereo center? And then if yes, then you have to reflect the racemic stereo center creation there. Now down here, you can see this became a carbonyl, and this primary alcohol, this secondary alcohol became a ketone, but this primary alcohol became an aldehyde, and we need to provide what reagent facilitated this oxidation. It's either going to be one of these two, and I think you're seeing it's going to be PCC, because of the fact that we didn't get a carboxylic acid in our product. We got the more mild oxidation, not the more aggressive. Okay, gang, like I promised, this was a short one. So if you're watching this video, thank you for supporting jOeCHEM. One, just for using it, and I hope it's helpful, but that means you financially supported the website, and I just truly and honestly and earnestly wanted to say thank you. I'm so happy you're using jOeCHEM right now on your quest to conquer carbon. I hope you're using it towards the end of OCHEM 2, or if you're watching this in OCHEM 1, OCHEM 1. But I hope to see you all in the next video.